Hello everyone. In the previous lecture, we have been dealing with the notion of orders, and uh, we started with this group Z mod nz, which we have been studying for a while, and then I mean, prior to this lecture, we had already seen the notion of order. I think the notion of order of an element of a group. So by now there are two notions of order that we know. One that we introduced in the last lecture, which is the order of an which is the order of an element. Which is the order of an element X of a group G, and there is something that could be the. There is another notion of order that measures the cardinality. So we can start with a group G, then its order denotes its cardinality. If you have a subgroup H of a group G, then the size of H is called the order of H, and so on. Okay. So yeah. So whether you're looking at the order of whether you're looking at order of G or order of something like H, or order of some element like G or X or Y. So based on that, we need to decide what does this I mean to what does this order refer to. Okay. Order of an element, usually elements of a group are denoted by small letters. This is customary, and a group or a subgroup is usually denoted by a capital letter, right? So yeah. So there is not much room for confusion though. Okay. With some amount of care, one can move ahead. There is one important result that we have stated in the previous lecture, which is known as the Lagrange's theorem, which says that the order of a subgroup divides the order of a group. Okay. So of course, it's much safer to assume that the ambient group is finite. Okay. Even if the ambient group is not finite, then some version of this statement also makes sense. Okay. Some appropriate version of this statement, or how to say, you can assume that this statement can be there is a statement even in the context of infinite groups. Okay. There is a statement even in the context of infinite groups that can be thought of as the analog of this statement, that the order of H divides the order of G. Anyway, so we will not consider analogs of this theorem in the context of infinite groups. Okay, at least as of now. So let's focus only on the finite group case, and let's move on. So applying this theorem, lots of results can be proved. A well-known such instance is the statement that any group of prime order is cyclic. Okay, great. So let's again get started with the group Z mod nz. Okay. So on this, one can also define something called the multiplication law following the same strategy. Okay. So you take two equivalence classes. Okay, and then you define their product to be the equivalence class of the product of two representatives, product of the representatives of these two classes. So what do I mean by that? So if you start with an equivalence class C, or you start with an equivalence class D, then their product C times D is defined to be the, let me write, equivalence class of C, equivalence class of the integer CD. Okay. uh, where C is chosen from C and little d is chosen from little d. Maybe this is not that clearly visible. Equivalence class of so note that this can also look like D. So let me rewrite it. So equivalence class of the integer C times D. Okay, so where C comes from C and D comes from D. But the point is that there are several choices for C, several choices for this element little c and little d, right? So you never know whether the equivalence class of C times D is going to depend on the choice of the element C from C, and on the choice of the element D from D. So here you may say that from in this definition there is no trouble. I mean, apparently it appears that there is no trouble, but there is some trouble, because from here you cannot extract A. Okay, uh, I mean, this only gives us, see, a bar is not, I mean, a bar is a set. Okay, so do not be under the impression that you first took a and then you are taking a bar, and even after taking a bar, this even after taking a bar, it carries the information that you have started with a. No, it is not the case. Okay, so we are not carrying the information that we have started with a, we are just carrying the information that the set a bar has. Okay, so for instance, uh, yeah, for instance, we can get started with some easy example. Yeah, maybe in the context of Z mod 2Z. uh, so you can get started with maybe 1 bar. Okay, there are not much examples though, so maybe you get started with 1 bar and 0 bar. So you can define it to be 1 bar, I mean the equivalence class of 1 times 0, right? On the other hand, note that 1 bar is also same as maybe 5 bar, and 0 bar is also same as maybe 12 bar. Then that product can also be defined as the how to call it, as the equivalence class of 5 times 12, right? The congruence modulo 2 equivalence class of 5 times 12. Okay, so the point is that, the point is that if you're given this set 1 bar, you do not know whether to pick 1 or to pick 5 or to pick maybe 7. Okay, so there is the confusion. Okay, but again, earlier we had similar troubles in the context when we are trying to define the notion of addition, and we saw that, the trouble is only apparent. Okay, so the trouble actually disappears. One can argue. Okay, even in this case also one can show that this composition law, as we have defined above, uh, uh, okay, is well defined. Okay, so by that I mean, if a bar is equal to c bar and b bar equal to d bar, then one can show that the equivalence classes of ab and cd, they're the same. Here I should make a remark. So let me not call it a composition law, let me just call it multiplication law. There are some reasons. Any idea why? uh, mhm. Sorry. So yeah, I have certain reservation for this term composition law for some reason. Let me just give me a moment. Let me move on to the definition of group. Just wanted to see whether I think I did mention the terminology composition law, right? Okay, yeah, I did mention the terminology composition law. Okay, so this is the first instance where you first this is the first instance where you met the term composition law. Okay, and I mean, okay, and from this one might be under the impression that this term composition law applies only in the context of groups. Okay, and yeah, so this definition might give the impression that the term composition law applies makes sense only in the context of groups, but only in the context of groups, and in that case, using the terminology composition law here could lead us to certain troubles, because Z mod and Z does not form a group in general under this multiplication law. One can show that. Okay, yeah, so this is just a, this is just a map from, let me just write G cross G to G, where G is Z mod and Z. Okay, so this multiplication law that we have defined above, this is a function from G cross G to G, that's all. Okay, so this is not a composition law, and one can show that G does not form a group under this law that you have defined, where G is Z mod and Z. Okay, so this does not form a group for this does not form a group for all n greater or equal to 2. Okay, the set Z mod nz does not form a group under the multiplication law that we have defined from G cross G to G, where G is Z mod nz. One can show that. Okay, so therefore I probably will try to refrain myself from using the term composition law, or at least I should have done that. Let me just call it multiplication law. Anyway, great. So the anyways still the multiplication law has certain has some group like properties, two of them being or I mean multiplication law has certain uh, I mean enjoy certain properties, enjoy certain properties that we have already seen in some other contexts. For instance, it enjoys associativity property, it is commutative, and so on. So one can verify that. Okay, this is not too difficult. I leave this as an exercise for you. Okay, yeah, and now we'll show that. You are already discussing that Z mod nz forms a group under the composition law, but we mentioned that it does not form a group, right? We mentioned that Z mod nz does not form a group under the multiplication law for n greater or equal to 2. However, we will show that we will show that certain subset of Z mod nz forms a group under this multiplication law. Okay, so what do I mean by that? Okay, so it will take a while to write, so let me write. Okay, we defined we defined law of multiplication on Z mod nz, right? And we are saying that this subset forms a group, right? We're saying this subset forms a group under the multiplication law. Okay, so we are restricting this multiplication law to this subset, right? Yes. uh, Anyway, you may also say that I haven't even introduced the definition. Yeah, I haven't, but let's not focus on the definition right now. Let's just try to understand this part, that subset forms a group under the multiplication law, whereas this multiplication law is not defined on the subset, is defined on a bigger set. So what I'm trying to point out is the following. We need to we have this uh, we have this law of multiplication, okay, on Z mod nz. More precisely, this is a function from Z mod nz cross Z mod nz to Z mod nz. Okay, then if you have a function from a set x to y, then certainly that function can be restricted to a proper subset of of the domain, right? So as we have just mentioned that this is a subset of Z mod nz, so one can definitely restrict this composition law to this subset. More precisely, I mean that one can restrict this composition law to the subset Z mod nz cross times Z mod nz cross. So one can restrict so one can restrict this function defined on this set to this subset of the of this one. Okay, to this yellow subset of the blue one. Okay, and then to say that Z mod nz cross forms a group under this, we need to make sure that the image of this function, the image of this restriction function, lies inside the subset Z mod nz cross of Z mod nz. Okay, the point is that if you pick two elements from here and multiply them using this multiplication law defined above, you end up getting an element of Z mod nz, right? So it is not apparent, it is not clear that it will land within Z mod nz cross. If it doesn't land within Z mod nz cross, then Z mod nz cross will not form a group under this composition law, right? So the point is that this has to land within Z mod nz cross. So it is guaranteed that if you pick two elements from here and multiply them using this law, then the answer or the product will land in Z mod nz. But you have to make sure that the product lands within Z mod nz cross. Okay, that's the very first step. In other words, you're trying to show that the restriction of the multiplication law, or maybe this multiplication law, is actually well defined. In other words, you pick two elements. pick one element from Z mod and Z cross and pick another and multiply them, you should land within, I mean, the product should land within Z mod and Z cross. Okay. Anyway, let's move on. Okay, great. Yeah, so then what is Z mod and Z cross? So there's a name attached to this. This is called the group of units of Z mod and Z. This is the name. I do not want to justify this name much because here this Z, I mean, here Z, I mean, what you see, it is not a, it is, I mean, this is not a group. Okay, this anyway. So let's just not try to understand the meaning of this phrase. Accept this as a name. So just to be on the safer side, let me put it within quotes. Okay. uh, Probably you say, you have a feeling that I'm trying to hide some information from you. Yeah, it is true. uh, to be able to make sense of this sentence or this phrase, one needs to know certain notions. Okay. That I haven't introduced as of now. So let's just accept this phrase as a, I mean, this is a single phrase without making any, I mean, without making any effort to understand the meaning of this phrase. Okay. So it will be great if you could to keep in mind that the Z mod and Z cross is called the group of units of Z mod and Z, but the specific terminology would not be of much use and in fact would not be of any use. Okay. Anyway, so now it is time to define define the subset Z mod and Z cross. So this is a subset of Z mod and Z. Okay, consisting of the elements A bar such that there is some B bar such that their product becomes 1 for some B bar inside Z mod and Z. Okay, this B bar, let me highlight that this B bar depends on A bar. Okay, so this B bar is not unique. I'm saying that they should hold for some B bar inside Z mod and Z. Okay. Anyway, so the first point is that if you pick two elements, I mean, from Z mod and Z cross, then their product, I mean, whether their product lies inside Z mod and Z cross or not. Okay. So the answer is it does, because you need to show that this is a group. No, sorry for this quote unquote how to say, quote unquote reverse way of arguing. Yeah, I mean, from the given statement you cannot conclude. We are asked to show. Yeah. Anyway, so you pick two elements A bar and C bar from Z mod and Z, then it is clear, I mean, it is easy to see that their product lies inside Z mod and Z cross, because we have taken A bar and C bar from Z mod and Z cross. So there exist elements B bar and D bar such that A bar times B bar gives you 1 bar and C bar times D bar gives you 1 bar 2. Okay, and then one can show that AC bar times BD bar, okay, AC bar, that is the product, this A bar times C bar, this A bar times C bar multiplied by something. Okay, so multiplied by something, by that I mean multiplied by BD bar, that is multiplied by the equivalence class of the integer BD, gives you 1 bar. Okay, so this is the claim, and this is easy to see using the associativity and commutativity property of the multiplication law. Okay, so this is something that I have just stated. Please work on it. Okay, as an exercise. Okay, great. And now that we have showed, now that we have established that this is a well-defined map, so now there are 3 more properties to verify, right? Yeah, so namely the associativity property, and then the quote-unquote the existence of identity. I am saying quote-unquote the existence of identity, because one can't talk about an identity unless one has proved that something is a group. Okay, and we haven't yet proved. We are just in the process of proving that Z mod and Z cross is a group. Okay, so don't talk about it. So I mean, we are not allowed to talk about identity elements, but again, this works only as a slogan. Okay, so for the associativity, I mean, there is not much to do, because associativity holds for any 3 elements A bar, B bar, C bar inside Z mod and Z. So if you take A bar, B bar, C bar from this subset Z mod and Z cross of Z mod and Z, then the associativity is going to hold for sure. And now note that if you pick the element 1 bar, then A bar times 1 bar is the same as 1 bar times A bar, which is equal to A bar for any A bar inside Z mod and Z, and in particular for any A bar inside Z mod and Z cross. And now if you pick an A bar, if you pick an element a bar from Z mod and Z cross, then then there certainly exists an element b bar inside Z mod and Z, such that a bar b bar lies inside 1 bar. You need to just observe that b bar is necessarily is b bar is not only an element of Z mod and Z, it is an element of Z mod and Z cross. Okay, that is very easy to see using the commutativity. So since you have that a bar times b bar is 1 bar, you know that b bar times a bar is also 1 bar. So by definition of Z mod and Z cross, b bar lies inside Z mod and Z cross. So let's recall the definition. It's a bit up, I'm sorry. I mean, some element of Z mod and Z, okay, some element of Z mod and Z lies inside Z mod and Z cross if that element times something else gives you 1. Okay, if that element times something else gives you 1. Okay, something else by something, okay, need not be something else, it could be the same element A itself. So here b bar is an element of Z mod and Z, and b bar times something gives you 1 bar. Okay, so b bar has to lie inside Z mod and Z cross by the definition of Z mod and Z cross. Okay, and on the so you have proved that so by definition of Z mod and Z, you picked an element a bar from Z mod and Z cross, and by definition of Z mod and Z cross, you obtain this element b bar having certain property, and then you prove that b bar lies inside Z mod and Z cross. Okay, and we had that a bar times b bar is 1 bar, and we need to show that something times a bar also gives you 1. That we have already seen once again here. So you have that a bar times something, and then something times b a bar is equal to 1 bar, where the element 1 bar of Z mod and Z cross had the property that a bar times 1 bar is 1 bar times a bar is equal to a bar for any a bar inside Z mod and Z cross. So you are done, right? So you are done. So we have established that Z mod and Z forms a group under the multiplication law that we have defined. Yeah, we usually say that under multiplication. So I have already omitted the word law from here. Anyway, great. So this is something important to keep in mind. Now let's discuss a bit about discuss an equivalence relation that can be defined on a group in general. Okay, so earlier we have defined an equivalence relation on the group Z. Okay, namely the congruence modulo n relation, and now we are going to define equivalence relation on a group in general. Okay, yeah, so you start with a group G and pick a subgroup H of G. Okay, we start with this much data, and then we are going to define an equivalent. Okay, we are going to define an equivalence relation, but while defining we can't call it an equivalence relation, we have to just say that this is a relation. Okay, so you define a relation on G as follows. So for two elements A and B inside G, we say that A is related to B if B inverse A lies inside H. Okay, now the very first observation is that this is reflexive because G is related to G. Okay, to show that G is related to G, we need to show that G inverse G lies inside H, right? But which is the identity element, and that has to lie inside H because H is a subgroup, right? Okay, great. And now that if you assume A and B are, now if you assume that two elements A and B of the group G are related in the sense that A is related to B, then in other words you are assuming that B inverse A lies inside H, and now you can invert it. Okay, you can claim that the inverse of this element lies inside H because H is a subgroup. Okay, since H is a subgroup, so the inverse of this element, so the inverse of B inverse A is A inverse B, that lies inside H. So that is something that we can say, and that proves that B is related to A. Okay, so we have established that this is symmetric. Okay, so now note that if you pick three elements A, B, C from the group satisfying these two conditions, that A is related to B and B is related to C, then we know that B inverse A and C inverse B has to lie inside H. Okay, and since H is a group, so you can multiply these two elements. Okay, so you know that C inverse B times B inverse A, C inverse B times B inverse A, that has to lie within H, and C inverse B times B inverse A is equal to C inverse A. Okay, and that is same as proving that, I mean, is equal to C inverse A, and you have proved that C inverse A lies inside H, and that is same as proving that A is related to C. Okay, so you have proved the transitivity property of this relation tilde that we have defined a while ago. So in other words, we have proved, I mean, so summarizing all these three steps, that this is reflexive, symmetric, and transitive, we can conclude that this is an equivalence relation on the group G. Okay, and now once you have an equivalence relation on a set, that makes sense. I mean, it's an interesting thing to make an attempt to describe the equivalence classes. Okay, so we'll try to describe the equivalence classes under this equivalence relation tilde now. Okay, so this is done in this lemma. So this says that for any element G inside G, the equivalence class of G under the equivalence relation tilde is a set little g times H. This is only a notation. Okay, and this is defined to be the set consisting of elements of the form G times H, where H lies inside H. Okay, the equivalence class of G consists of all the multiples of G, by elements of H from the right. Okay, that's the point. So sometimes this is phrased in words as I have just stated, as follows: that the equivalence class of G under the equivalence relation tilde is equal to the set consisting of the product of consists of the product of G by element consists of the products of G from the elements of by elements of H from the right. Okay. It consists of the products of G by elements of H from the right. Equivalence class. So this equivalence class of G, the equivalence class of G consists of the products of G by elements of H from the right. Okay, great. So now it's time to prove this lemma. So pick an element G from G, and note that if you have an element G prime, okay, of G such that G is related to G prime, okay, then you know that G prime inverse times G has to be an element of H. In other words, G prime inverse times G is equal to little h for some little h inside H. Okay, and then it follows that little g has to be equal to G prime times H, right? And that shows that G prime is equal to G times H inverse. Okay, so this element G prime is of the form G time an element of H. Note that H inverse is also an element of H, right? Because H is a subgroup. So this element G prime lies inside the set GH, which is defined to be the set consisting of products of G by elements of H from the right. Okay, so I mean, this follows after observing that the element H inverse also lies inside H. Okay, so you have proved that G prime lies inside H. In other words, whatever element of G that you pick, if G is related to G prime, then that element G prime has to lie inside GH. Okay, in other words, the equivalence class of the element little g is contained inside GH. That is what we have proved. And now note that if you pick an element from GH, that okay, just let me make a remark. How to so you have proved that the equivalence class of G is contained inside GH, right? And now we need to show that any element of GH lies in the equivalence class of G, that is, G is related to any element of GH. So let's pick an element of GH denoted by G double prime. So G double prime is of the form G times H double prime for some H double prime inside A, and then from this it follows that G double prime inverse times G is H, it's H double prime inverse, and so it follows that G double prime inverse times G is an element of H. So it follows that G is related to G double prime, and that is something, this is a statement that we have proved for any element G double prime of GH. So you have proved that any element of GH is contained inside the equivalence class of G. Okay, So thus the equivalence class of G under this equivalence relation that you have defined a while ago is equal to this set GH, which consists of the products of G by elements of H from the right. Okay, great. So now it is time to define something interesting. Okay, so suppose H is a subgroup of a group G, then a left coset of H in G is a subset of G of the form little g times H. So such subsets are very special in the study of groups. So they are usually called the left coset of H in G. So they have a special name. So these are called the left cosets of H in G. And now if we have a subgroup, similarly, for a subgroup H of a group G, if you pick an element, then we can reverse the picture. We can take the products of G by elements of H from the left. So you can look at this set. You can look at the products of G by elements of H from the left, okay? And this is denoted by capital H times G, okay? And as you may guess, since little g times H is called the set of a left cosets, so this makes perfect sense to call this set call a right coset of H in G. Okay, a right coset of H in G is of the form capital H times G. Okay, great. And now we are in a position to prove. Lagrange's theorem. So start with a finite group G and the subgroup H of that, and I'm going to show that the order of H divides the order of G. Okay, so we start with the equivalence relation that we have been studying for a while. So we start with the equivalence relation tilde, and then we know that the equivalence classes of tilde, that is the distinct. So recall that the equivalence classes are of the form little g times H. That is, the equivalence classes are left cosets. Okay, so we are going to focus on the distinct equivalence classes, right? We know that the distinct equivalence classes, that is the distinct left cosets of H in G, they form a partition of G, right? So the order of G has to be equal to the sum of the sizes or sum of the cardinalities of the distinct left cosets. Okay, so suppose suppose there are 10 left cosets, so then you have to just add the cardinalities of those 10 left cosets to get the cardinality or the order of G, right? And so now you will show that the cardinality of any left coset of H is equal to the cardinality of H. Okay, in other words, we are trying to show that the size of or the cardinality of any two left cosets, they are equal. Okay, and this order of G is sum of the cardinalities of distinct left cosets, that is sum of certain integers, right? So these integers are the cardinalities of the left cosets, and we are claiming that the cardinality of any two left cosets, they are the same. Okay, so and in fact they are equal to the cardinality of H. Okay, that is immediate that the order of G is equal to the cardinality of H times the number of distinct left cosets. Okay, times the number of distinct left cosets. Yeah, here you have an integer which you have expressed as sums of some other bunch of integers, and you are proving that we will show that those integers, they are all the same. Okay, and they are in fact equal to the size of H. Okay, yeah, this is actually straightforward. So we have a so you need to just show that if you pick a left coset of H, so which is of the form little g times H for some G in G, and so to show that little g times H and capital H, they have the same cardinality. So this can be done by establishing a bijection from H to GH, and that is straightforward. You pick an element H from H and send it to little g times H. One can show that this is injective and surjective. Okay, and then you will be done. So you claim that this is a bijection. Why? So first of all, one can one can show that this is injective, and then one can show that this is surjective. Again, this is an exercise that I leave to you. Okay, and then as I have just been explaining, from that it follows that I cannot write the order of G is equal to sum of cardinalities, I hope the spelling is essentially okay, cardinalities of the distinct left cosets, and So whatever left coset that one may have in mind, its cardinality is same as the cardinality of H, right? As you have just stated, its cardinality is same as the cardinality of H. So the sum is equal to size of H plus size of H taken few times. Okay, how many times is equal to the number of times that number of, I mean, the size of H is repeated as many times as the number of distinct left cosets, right? So this order of G has to be a multiple of size of H or multiple of the cardinality of H. In other words, multiple of the order of H, and that proves this claim or this theorem of Lagrange. Okay. And here there is one thing to note that yeah, as I stated that this map that you have just defined is a bijection, okay, and I haven't proved. So this is left for, I mean, left to you as an exercise, okay, to show that this map that you have just defined is a bijection as claimed, okay. So anyway, so I was just highlighting this exercise. Now here are a few examples / exercises for you. It's good to think about. So you could show that no group of order 20 contains subgroup of order 21. Okay. And okay. So now, okay. So now we try to go back to what we have been doing. So we earlier defined the relation, and we showed that there is an equivalence relation, and we observed that the equivalence classes are the left cosets. Okay, the equivalence classes are the left cosets. Now here is an exercise for you. Can you define, or I'm asking you to define, can you define an equivalence relation on G? Okay, of course you start with the group G and the subgroup H. Then after that, can you define an equivalence relation on G such that the equivalence classes are the right cosets of H, okay, or something of this form, okay, instead of being little g times H, okay. Sorry, probably I just went too fast. So the equivalent, I would like the equivalence classes to be of this form, okay, instead of being left cosets, okay. Earlier we showed that the equivalence classes are, as in definition 104, right, they are left cosets of capital H in G, right. So now I would like to have an equivalence relation where the equivalence classes are right cosets. In other words, they consist of multiples of G by elements of H from the left, okay. Okay, great. And so I'd like to have one such equivalence relation, and then again I'd like to have a proof of Lagrange's theorem using this equivalence relation, okay. So try to work on this exercise, okay. Yeah, so now there is a few more exercises. So you consider these two exercises are somewhat, you may call them somewhat vague, or at least somewhat vague, okay, or you may also call them imprecise. Yeah, they're so while developing some notion or certain ideas, one may, it's fine to have certain naive thoughts. I'm just trying to motivate some of the upcoming notions. Okay, so you consider the group mu(n) of nth roots of unity and the group Z mod nz. So do you think that these two groups are really different, or they have some sort of similarity? Okay, this is a nice question, so try to answer this question to yourself only. Okay, and you may have, different answers, okay. Anyway, so you also maybe have the group U2R in mind, and then the question is this group U2R really different from the group of real numbers? Okay, yeah. So please try to work on, or to think about these two exercises and the earlier exercises, and go through the proof of Lagrange's theorem, and whatever you have been discussing, whatever you have discussed today, and whatever we have been discussing, because we are going to use these notions of, for instance, subgroup, order, cyclic subgroups, abelian groups, Lagrange's theorem over and over again. And these groups Z mod nz will appear very often. Okay, certainly the other groups will also be there, like mu(n) or U2R or M2R or MNR or GLNR, something like that. Okay, so please go through all this content and make yourself familiar with these notions. Okay, let's conclude here.